Hi, hello everyone. I'm Minoru Asada, a professor of Osaka University Graduate School of Engineering. Today, I'd like to introduce the main achievement of our research project, officially JSPS Grant Aid for Specially Promoted Research, entitled Constructive Developmental Science, based on the understanding of the process from neurodynamics to social interaction. It's a little bit long title, but the main purpose is to establish the constructive developmental science, a transdiscipline involving diverse scientific fields, by using the constructive approaches with robots and artificial systems, especially focusing on understanding of the human's cognitive development process from neurodynamics to social interaction. Constructive developmental science attempts to address these issues by means of synthetic approaches based on computer simulations and real robot experiments, expecting to obtain the new insight for them. A fundamental neural architecture develops with physical environment through the social interaction. During the process, learning methods are applied and the functions as goals or assumptions differentiate. Today, we will show the fundamental neural architecture for various behavior emergence, the predicate coding for robot behavior generation, human brain imaging studied for social interaction, and finally, the robot platform study. How can we generate many kinds of behavior? We assume that the diverse behaviors will emerge from the coupled dynamics between the brain and the body in the environment. In our research, we show that the diverse behaviors and their transitions emerge from the coupled dynamics among simple nonlinear oscillator network, musculoskeletal model, and the environment. Moreover, we revealed that the structure of the network behind the coupled dynamics to induce the bodily chaotic itinerancy. Based on the nonlinear principal component analysis of emergence behaviors, the movements are mapped onto the 2D plane, where red, green, and yellow-green indicate the stable movements, while the blue shows the unstable one. In the future, we are planning to apply more complicated model and detailed analysis for the new understanding about the emergence of the bodily chaotic itinerancy from the coupled dynamics. We advocate a cognitive developmental theory that diverse social behaviors such as self-other cognition, imitation, and altruistic one develop based on the predicate coding for sensory-motor contingency. It's a common framework in computational neuroscience attempting to explain various cognitive functions. The predicate coding is a mechanism which minimizes the predicate error, that is, the difference between the bottom-up signal from the environment and top-down signal predicted in the brain. It is supposed to be an essential function in the human brains. Especially, we suppose a two-stage learning process. At the first stage, infants born with immature predictors attempt to minimize their prediction errors by measuring their predictors based on their own sensory-motor experiences. During this process, we assume that they gradually acquire the capability for self-other discrimination, that is, the discrimination between the things they can control and they cannot do. The second one is a stage where agents predict others' behaviors based on their matured predictors, and their social behaviors emerge. We advocate that the self-induced movement triggered by detected prediction errors minimize them, and consequently such movements lead to social behaviors such as imitation and helping behavior. Today, we will show the prediction for others' movement and the emergence of the helping behavior. ICAP learns two kinds of movements, that is, pushing a blue car through its visual and smart sensory perception. Then, ICAP predicts the other's motion based on its own predictor. As explained before, ICAP attempts to minimize the prediction error, and as a result, it became helping behavior. That is, the primitive social behavior emerges. We advocate that behind various kinds of social behavior, there is a simple mechanism of prediction error minimization, which is a unified framework that emerges such diverse behavior. In CNET, we are investigating neuronal mechanisms for sensory processing, motor control, and motor learning using MRI and behavioral approaches, mainly in adults' brain. In this project, we focus on the issues of self-other recognition and predict motor control. In order to conduct the series of studies, we first built research environment for MRI scanning in children here in CNET, and we have started child MRI since July 2014, after the approval of the ethical committee of NICT in April 2014. We investigated how self-other recognition develops by focusing on neural processing of self-face, which is a symbol of the self. We found that the elementary school children could discriminate their own faces from others like adults. However, the brain activation patterns were largely different between children and adults. We also found in adults that the front parietal activity was lateralized to the right hemisphere, and these regions were commonly used for perception of one's body image. Such common use seems to emerge at around junior high school age. Thus, the right front parietal activity can be a biomarker for the maturation of the self. In future, we will elucidate how human brain acquires functional differentiation during the development. We examined how predictive motor control develops. We found both children and adults can perform one healthy movement, but the variance of the movement timing became greater in children. We found weaker cerebral activity. In addition, we found that the brain activity was suppressed in the visual cortices and default mode network in adults' brain, which was not the case in children. This type of mutual suppression between information networks can be considered as a functional specialization in adults' brain, which is not yet measured in child's brain. From now on, we elucidate the dynamics in the development of such a neuronal suppression between information networks, which should be promoted after the childhood. Now we are at the Kanazawa office, a Ricoh Company Limited. And here we have the first hyperscanning MEG system in a single sealed room, and may contribute to elucidating the brain-to-brain interactions, not only between the mother and her child, but also in general, inter-individual brain-to-brain interactions. In these 7 years, using a custom-sized whole-head MEG system, we measured the brain activity both in typically developed children and children with autism spectrum disorder. We measured MEG mu suppression during face-to-face spontaneous non-linguistic interactions between mothers and 4 to 7-year-old children with ASD. The mu suppression level of the ASD children and their mothers reflects the social ability or autistic traits. Robot Platform Group is studying on the bodies of the communication robot as interface between the robot's brain and humans. We regard the following 3 approaches as important. The first one is to learn from a child body. The second one is to functionalize soft materials to enhance the safe and rich interactions. And the third one is to analyze humans on how they feel and respond to the robot. First, I'd like to introduce a flexible and compact joint structure for the Android. We adopted pneumatically actuated joint system and developed a flexible and compact joint structure. The left movie shows how the developed upper body moves with 22 joints. Thanks to the rich joint with the softness, rough physical interaction is possible like this. The leg in the right movie has 10 joints, and these joints have softness as with the upper body. The robot needs skin. The left figure shows the structure of the developed sensor. We can estimate the surface deformation. The right movie shows the actual behavior of the sensor. Large responses are appeared against weak contacts. We have sorted out several problems and made two small face robots with soft skin that can show the several expressions, and we call this robot Affect. Real mothers spoke to Affect.
Monaro.
The right graph shows that the affect-directed speech was recognized as infant-directed speech by the third party. This speech style is considered to promote the social development of children. We measured flow vector fields for 16 deformations and analyzed them to find design guidelines for robot face. In addition, we investigated how robot surface touch changes its personality impressions and found that robot touch enhances or degrades its personality impressions. Thus, we have deepened the understanding of the robot body design for bonding humans and robots by learning from children, functionalizing soft materials, and observing the humans. Did you enjoy our research achievement? In this video, we have not introduced everything, but the researchers from different disciplines gathered to address the mystery behind the process from neurodynamics to social interaction. There are still many issues unsolved, especially a consistent pathway to link these interdisciplinary studies has not been found. After solving this issue, we will expand the constructive development science through the new insight into the human's cognitive development and design of interactive robot with people. We believe that we can contribute to our future symbiotic society with artificial systems.